Now we're going to talk about the concepts of basis and dimension. Before I do that, let me say a couple more words about linear dependence and independence. So the setting is, suppose we're in Rn, and if you give me n vectors v1 through vn, the question is, how do you tell if they're linearly independent? And the answer is you make them into a matrix v1 through vn, and you check whether the determinant of that matrix is not equal to 0. And here I'm thinking of these as column vectors. It's vector v1, v2 through ... vn. Now, of course, if you thought of them as row vectors, it would be exactly the same thing. If you think of them as being rows, that's just the transpose matrix. And it's exactly the same question. So here I'm thinking of them as being rows. And that's what you do if there are if you have exactly n vectors in n space. Now, what if you have fewer than that? What if you only had m vectors in Rn? And Professor Schaefer talked about this, and I'm just going to flip what he said and make them rows. You take these vectors v1 down to vm, and I'll write it like this to indicate that this is an m by n matrix. And as Dr. Schaefer talked about in class, if you do row operations, that doesn't change the property of linear dependence or not. So row operations are allowed, and by that I mean if you add any multiple of one row to another row, it doesn't change whether those vectors are linearly independent or not. Similarly, switching rows and multiplying rows by a non-zero constant. And so what you do is you apply Gauss to this, Gaussian elimination, and you see if you get any zeros, any rows with all zero. If you get a row of all zeros, that means that they're linearly dependent. Well, I want to do one little variant on what I just said. And now suppose you're in Rn, and you had m vectors in Rn. And before I talked about what you do if m is less than n. And let's talk about what happens if m is bigger than n. So the same thing works. And what I'll do is I'll draw the matrix sort of suggestively this way. You write v1 down to vm, and the number of rows here is m, and each of these is an n vector. And you do Gaussian elimination on this, and you see whether you get any zeros. Well, what happens when you do Gaussian elimination, you get an upper triangular matrix, so to speak. I mean, it's not a square matrix, but that's okay. You're going to get a matrix which looks like this, and it has some a1 down to am down here, and anything up here, and zeros here, and in fact, it's going to be all zeros down here. This section is going to be all zeros. And therefore, these vectors are definitely not linearly independent. So that's a basic fact. So that's a basic fact. If you have m vectors in Rn, where m is bigger than n, then they are not linearly independent. And let's just draw a little picture to illustrate in R2. For example, if m is equal to 3 and n is equal to 2, if you have 3 vectors in R2, well, let's say you have your first vector v1 and a second vector v2, then no matter what your third vector is, it's in the span of v1 plus v2. v3 is some a v1 plus b v2, and that tells you that they're not linearly independent. So if you think about it, what I just said is that in R2 you can find at most 2 linearly independent vectors. And furthermore, if you give me 2 vectors, then they're linearly independent exactly when they span the whole space. Right? So if you give me 2 vectors pointing in not the same direction, they're linearly independent and they span all of R2. Whereas if you give me 2 vectors in the same direction, then they're not linearly independent, and that's because they don't span all of R2. And that leads us to the concept of basis and dimension. So a basis of a vector space, I'll give that definition now. Basis of a vector space is a set of vectors with 2 properties. First of all, they're linearly independent. And they span the whole vector space. So back in this example, these 2 vectors are a basis, and these 2 vectors are not. What happened there? These 2 vectors are not a basis. So notice that, for example, well, I'll do one little example here. In R2, what's the basis of R2? It has to be a linearly independent set of vectors. Well, so it has to have at least 1 vector in it, so let's put a vector in it. And is that a basis? Well, no, it doesn't span of all of R2. This only spans a line. So you better add another vector to it, and it had better not be in the same direction. There's another vector. And now this is a basis because they're linearly independent and they span all of R2. And one of the key points is that it's sort of obvious that to find a basis of R2, it always has exactly two vectors in it. And that leads to the notion of dimension. If V is an abstract vector space, then the dimension of V is the number of vectors in a basis of the vector space. So that's a bit of an abstract definition. You have an abstract vector space. The dimension is the number of vectors in a basis. So the dimension of Rn, of course, is n, because a basis of Rn is the following vectors: 1, 0, 0, 0, 0, 1, and so on down to 0, 0, 1. I claim this is a basis of Rn. Well, are they linearly independent? Yes, because if you make a matrix out of them, you get the identity matrix. And the determinant of the identity matrix of size n is equal to 1, which of course is non-zero. So they are linearly independent. And do they span? Can you get every vector in Rn as a linear combination of these vectors? And the answer is yes. If you have any vector, you can write that as a1 times this first vector plus a2 times the second. Oops. 0, 1, and so on down to an times the last. So that's, of course, a crucial property of this notion of dimension. It would be kind of ridiculous if the dimension of Rn came out to be something different. And the point of this is that this abstract definition, when you apply it to this concrete case, is giving you the number that you expected. But this abstract definition works for an abstract vector space. Well, let's think about the same problem in a slightly different way. I have these two vectors v1 and v. If I have two vectors v1 and v2, I can make them into a little 2x2 matrix, v1, v2. These are two vectors. And the condition that this is a basis, let's write out this matrix as a 2x2 matrix, A, B, C, D. The condition that it be a basis is exactly the condition that the determinant of this matrix is not equal to 0. And if you think about that, that's almost always the case. If you write down a random matrix, the chances are that it has this property. And in some sense, almost all matrices have this property. So there are lots and lots of bases. You should think of bases as not being unique at all. There's many, many, many possible bases of any given vector space. So here's one useful fact about bases. if you have suppose you have a set of vectors v1 through vn, then this is a basis if and only if any vector w in V can be written uniquely as a linear combination of these vectors, which is to say in the form a1 v1 plus dot 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 plus a n v n. So a set of vectors is a basis if and only if every vector in the vector space can be written uniquely as a linear combination of those. And why is that? So why is that? So remember, it's a basis if and only if, first of all, they span, and second of all, they're linearly independent. Now, what did I say up here? I said it's a basis if and only if there are two conditions that hold. W and V can be written, that's condition 1, as a linear combination, and it's a separate fact that that is unique. So to say that a vector can be written as in this form, that's exactly the span condition, right? A set of vectors span the vector space if every element of the vector space can be written as a sum like this. So that's condition 1 is condition A. And then the condition 2, I'm saying, is exactly the same thing as condition B, the uniqueness. So I'm saying that if you have a set of vectors which span the vector space, it's unique if and only if they're linearly independent. So if V1 through Vn span, I'm saying that this expression is unique if and only if it's a basis. Why is that? Well, if it's not a basis, that means you have extra vectors, and there's more than one way to write this sum. That's just roughly. So I suggest that you pause the video here and think about why B is really the same thing as 2. The uniqueness is really the same thing as linear independence. And we'll talk about that in class.